Talen-X would like to introduce you to the newest addition to the Broad Sense product line. This is Broad Sense Nano, the smallest size, weight, and power Broad Sense ever built. What you are looking at is actually a prototype. The real version will be even smaller. Broad Sense Nano is similar to its predecessors, but there are some new features that really set it apart. The most obvious of which is the screen on the front that provides real-time feedback to the operator. The most important information displayed on the screen is the jamming level indicated in dB of J to S, jamming to signal ratio. In prior versions of our product, we indicated that we were jammed. We've never had the ability to indicate how jammed we were. That is the most important new feature for Broad Sense Nano. Also, at the bottom half of the screen shows an L1 spectrum analyzer, which is 16 MHz wide. Today I would like to show you how Broad Sense Nano reacts to various jamming waveforms. To do this, I'm going to use BroadSim, our GNSS and jamming simulator. I'll start with some simple BPSK jamming on L1. We're going to be looking for how quickly Broad Sense Nano reacts to the change in jamming and how accurate it gets the jamming level. This first jammer should be 40 dB J to S. I've enabled the jammer, and we can see that Broad Sense Nano immediately reacts. It settles for a few seconds and determines that the current J to S is 40 dB. So this is very accurate. Let's keep increasing the jamming and see how accurate it stays throughout the entire jamming curve. So next I'll do 45 dB. Again, it reacts very quickly and settles to 45 dB. I'm going to keep going up by increments of 5. And we'll keep watching to see how well Broad Sense determines the amount of jamming. At 50 dB, we're still looking really good. Let's try 55. You can see that sometimes we overshoot by a couple dB for just a second or two. This is due to how the sensor works, but so far it's looking pretty good. Here's 60 dB. And 65 dB. All right, that's looking good. Let's try 70 dB. Now we are actually approaching the more difficult part of the curve. 70 dB is quite a bit of jamming, and the sensor struggles a little bit more in this region. So I'm going to go up by increments of 3 dB and show you the effects. You can see at 73 dB, we actually underestimate the jamming by a couple more dB than we have been before. Let's go to 76 dB. You can see that we're undershooting the jamming by about 3 or 4 dB right now. This is the weakest point on our jamming curve for us. Let's try 79 dB. 79 dB is looking much better. We're through the difficult part of the curve. Let's try 85. Now we indicate 84 dB. We're actually approaching the upper limit of our sensor's capabilities. As we increase the jammer, let's see what happens. At 90 dB, the sensor indicates that the J to S level is greater than 90 dB. This is our method of indicating to the user that we no longer know how much jamming we are experiencing because we have maxed out our sensor. You'll also notice that on L2 we've indicated less than 40 dB. This is because that at this high of a jamming level, we've lost the ability to determine the low power jammers on L2. The sensor provides feedback to the user indicating that we know it's at least less than 40 dB, but we can't determine any better than that. Let's do some larger jumps, and instead of going up linearly, we will try bouncing around a little bit to make sure the sensor correctly gets the J to S level. So I'm going to go back down to 50 dB. Now you'll notice it takes a few more seconds to settle down from the high power level, but fairly quickly the sensor does settle back at 49 dB J to S. I'm going to try 80 dB. And very quickly we go up to 79 J to S. And let's try a really low power jammer at 35 dB. You can see it takes a few more seconds to drop down so low from a high power jammer. And now it's indicating that the J to S is less than 35 dB. I'm going to switch over to L2 and do a few more examples. It should be basically the same as L1, but we'd like to demonstrate it. Let's start by going to 50 dB with a BPSK on L2. You can see that we overshoot for a few seconds, but we settle on 50 dB. Let's try 70. And we're settling on 71, 72 dB J to S. Let's try 80. And we indicate 81 dB. And let's try maxing out the sensor at 90 dB. And again, we've indicated greater than 90 dB. While leaving the L2 jammer on, I'm going to go back to L1 and try a couple values out here. Let's try 50 dB. So you can see that even when we're experiencing 90 dB of J to S on L2, we can correctly indicate 50 dB of J to S on L1. Let's try 70. And 90. And now we're indicating that both L1 and L2 have exceeded our sensor's capabilities. I'm going to turn these jammers off, and we'll see how long it takes to settle all the way from 90 to 0 J to S. You can see it's not immediate, but it is only a few seconds to get back down to less than 35 dB. Now I'd like to show you some different waveforms. We've been using BPSK so far, but does this sensor work for other types of waveforms? I'm going to do this on L1 so that we can actually see the spectrum as well. Let's start with the 50 dB BPSK just to remind ourselves what that spectrum looks like. You can see all the energy is concentrated in the center. You can even kind of see the lobe shape. Now I'm going to do a CW tone. All of these I will do at 50 dB J to S. So the sensor correctly guesses 50 dB J to S, and you can see a spike in the center. Let's try a chirp jammer. Again, you can see that we estimate 50 J to S. This is a very interesting spectrum analyzer shape. The energy is concentrated in the middle, just like the BPSK, but there is no lobe shape. And this is correct for the type of jammer a chirp jammer is. The strength should be the same across its entire bandwidth. Let's try a box signal. You can see we're at 50 J to S, and you can see the two lobes in the spectrum analyzer. Now I'm going to generate AWGN 1 megahertz wide. Now you can see we underestimate the J to S just a little bit for AWGN. You can see the shape in the middle there. It's not as strong as the chirp, but it's definitely 1 megahertz wide, and it's not a BPSK shape, so it does kind of look like AWGN. Let's try increasing the bandwidth to 4 megahertz. And you can see the shape is now flatter and wider. Let's try 8 megahertz. Now you'll notice the J to S doesn't change as I change the bandwidth. And lastly, I'll try 16 megahertz. We're probably not going to see much on the spectrum analyzer at this point. The shape is consistent with an AWGN at 16 megahertz, but we can't really determine that. It kind of looks like nothing's there. There's one more waveform I'll generate. This is a pulsed CW. Now in this example, we do not indicate the J to S value correctly. Let's try increasing the jammer power. So at 90 J to S, we indicate 40 dB. Now why is that? Well, the pulsed waveform is only present 10% of the time. Let's increase this percentage. So at 50% of the time, at 90 J to S, we indicate 63 dB J to S. I'm going to change it back down to 50 dB, and I want to increase the percentage to 75%. We're indicating about a 45 dB J to S. And 90%, 48, 49 dB, and 100%. And at this point, we should indicate 50 dB J to S. So it turns out that for the pulsed jammer, the sensor works fairly well. You just have to keep in mind that at 10% duty cycle, a 50 dB J to S waveform does not show up very strong. That's everything I'd like to show you today. Thank you for watching this video, and we hope that you try to evaluate Broad Sense Nano the next time you have an opportunity.